Today we're going to look at how to count the number of subatomic particles in an atom, depending on whether we are looking at the basic elemental form as represented on the periodic table, an isotope of that element, or a charged particle of that element, also known as an ion. So we learned that if we look at the periodic table's representation of element, like in the case of bismuth, we can work out the number of protons, neutrons, and electrons thusly. The atomic number is the number of protons. It is the proton number that gives an element's identity. If we see no other symbols with the atomic symbol, we're going to make an assumption that this is a neutral form of the atom and that the number of electrons and protons are the same. To determine the number of neutrons, we round the mass to its nearest whole number. So in this case, we've rounded the atomic mass to 209, and we subtract the number of protons, and that gives us the number of neutrons. Similarly, for iridium, we use the same method. Atomic number for iridium is 77, so thus we have an equal number of protons and electrons because we see no other symbols implied. We subtract the protons from a rounded mass, which in this case is 192, and we get 115 neutrons. However, very often we will see additional symbols and numbers with an atomic symbol that tells us we're not looking at the pure neutral elemental form of an atom as represented on the periodic table. When we see a number after a dash following an atomic symbol, that means it's probably one of the many isotope forms of that element. One more time, an isotope is a form of an element that has a different number of neutrons than another isotope of that element. So in this case, strontium-90 is a radioactive form of strontium that has a couple of more neutrons than the more common isotopes. So we have to pencil that value in as our mass rather than the periodic table version. We don't see any other symbols, so we assume that this is still a neutral atom with an equal number of protons and electrons, but we use this mass and subtract number of protons so we get the number of neutrons. Finally, when we see charge symbols, this means that we either have an excess or deficit of electrons relative to the number of protons. We're not assuming that there's a different number of neutrons than we would expect if we took the rounded mass and subtracted protons, but we are assuming a different number of electrons from protons. In this case, the selenide ion is a negatively charged version of selenium. It has picked up 2 extra electrons, so instead of an expected 34 electrons that we would see for a neutral atom, we add 2 more. Remember, this is a negative symbol, not a subtraction symbol. On the other hand, chromium, like most metals, takes on a positive charge. This 3 positive means that we have a deficit of electrons. So instead of a 24 electrons that we would normally see in a neutral atom, we only see 21. So once again, this is not addition or subtraction. This means positive or negative. In the case of ions, a positive symbol, which we normally think of addition, represents a loss of electrons, whereas the negative symbol, which we often will view as a minus, means an addition of electrons. So in closing, it's very important when you're looking at an atomic symbol to see if there are any other numbers or symbols that go with it, which tells us that we aren't referring to an atom of that element that takes on the base form that is implied in the periodic table. Also, recognize that isotopes can be represented different ways in textbooks. This is one common way. It's also very common just for textbooks and professors and academic papers to represent an isotope mass number as a superscript. And you will see that just as commonly as the first way. And finally, a third way shows the atomic mass on top of the isotope and then the number of protons, the atomic number, below it in a subscript. All three are equally valid, but you need to remember that all three might be used depending on a text or a professor who you may have, and just recognize that they're the same thing.